Hello everyone, welcome to the second video of this series. We will continue from where we left off. In problem 11, we have to find the function that could be represented by a Fourier series over this range. According to the Dirichlet condition, the function has to be periodic, so this eliminates option D. The function has to be bounded, this eliminates option A. The function must have finite number of discontinuities. The function is in option C has infinite number of discontinuities where cos of x is 0. So option B is the final answer. In problem 12, we are given two normalized eigenvectors phi1 and phi2 corresponding to two distinct eigenvalues of Hermitian operator A in two-dimensional vector space. In other words, phi1 and phi2 are orthogonal. We are also given an operator f which looks like this. Which of the following statements are true? So notice the operator f has phi1 at both the ends. So if we take the inner product with respect to phi2, this term will go to 0. The same thing happens in the other end where phi2 dot phi1 is equal to 0. So option B is the correct answer. Problem 13. A mass m is hung from a massless spring of spring constant k. When it is displaced by an amount a from its equilibrium position, it executes simple harmonic motion and the total energy is this. If the mass is doubled keeping the amplitude fixed at a, what would its total energy be? So for harmonic oscillator, omega square is equal to k by m, or m omega square is equal to k. Hence, the total energy is equal to half k a square, and it is independent of the mass and only depends on the amplitude. So if mass is doubled, the total energy would be same. So option D is the correct answer. If a particle of mass m is in a potential v of x given by this, then what is the frequency of small oscillations about equilibrium? Let's find the equilibrium position first. To find that, we take derivative of v with respect to x and equate it to 0. So let's find the derivative first. So this is equal to 2ax minus 2bx cube. Now solving this for x, we find x is equal to p by a to the power 1 by 4th. Now in near the equilibrium position, v of x can be approximated as v of double prime of x times x square. This is very similar to the potential of simple harmonic oscillator where the spring constant k is analogous to v double prime of x at the equilibrium position. So let's find the double derivative of v with respect to x. This is equal to 2a plus 6b x to the power 4. Now we substitute x is equal to b by a to the power 1 by 4 and simplify this expression to find out this is equal to 8a. Hence the oscillation frequency omega is equal to k by m and square root of that, which is equal to 8a by m. So option B is the correct answer. Problem 15. If the brakes are applied suddenly to a moving car, the wheels will skid. This is because the inertia of the car will carry it forward. So option A is the correct answer. Problem 16. An elliptical orbit equation of a satellite is given by this. We have to find the altitude of apogee and perigee. In apogee, cos theta is equal to -1. Hence r is equal to 8256 kilometer divided by 0.8, and in perigee cos theta is equal to +1, so r is equal to 8256 divided by 1.20. So we find that option B is the correct answer. The escape velocity from the earth is equal to 11.2 km per second. Consider another planet whose average density is 25% of that of the earth, but whose radius is 8 times larger. what is the escape velocity? So the escape velocity can be found by the following formula, where half of mv square, this is the kinetic energy, is equal to the potential energy at the surface of the earth, or v escape is equal to square root of 2 gm by r. Now the mass is proportional to rho density times r cube, so we put that in here, which simplifies to v of escape is equal to or proportional to r times square root of rho. Now v by v earth, we are taking the ratio of the escape velocity of the planet and that of earth is equal to r divided by r earth times square root of rho divided by rho earth. So given that this is 8 and this is 0.25, so we find the escape velocity is equal to 8 times square root of 0.25 times 11.2 kilometer per second, which is equal to 44.8. So option A is the correct answer. Consider the sun to be a uniform solid sphere of radius this, rotating about its axis with a time period of this. If it now shrinks to a sphere of radius 7 km but not losing any of its mass, what would its time period be? So we will use the conservation of angular momentum, which is I1 omega 1 is equal to I2 omega 2, where omega are angular momenta and i's are moment of inertia. So moment of inertia I is proportional to m times r square. Since mass remains same, so we found r square omega 1 is equal to r2 square omega 2. Now omega is proportional to 1 by t, hence we find r1 square by t1 is equal to r2 square by t2, or t2 is equal to r2 by r1 whole square times t1. Now putting these values, r2 is equal to 7 km, r1 is equal to 7 into 10 to the power 5 km, and t1 is equal to 25 days. We have to convert this to second. We find that the values of t2 is 2.16 times 10 to the power minus 4 second. So option C is the correct answer. Hubble's law is defined as v is equal to h naught times r, where v is the velocity of the galaxy and r is the distance, and h0 is called Hubble's constant. So we have to find the dimension of h naught square divided by g. So h naught is equal to v by r. So the dimension of h naught has inverse of time. Now to find the dimension of g, we use the formula force is equal to g mm by r square. The dimension of force is ml t to the power minus 2, and which equal to dimension of g times m squared divided by l squared. Let's m gets cancelled out, so we find the dimension of g is equal to l cube divided by m and t squared. Let's find the dimension of h naught square divided by g, which is equal to m t squared divided by l cube and divided by t square, so which is equal to m by l cube. This is exactly the dimension of density, hence option D is the correct answer. Which of the following equations is Lorentz covariant? So option is a wave equation. In relativistic notation, it is covariantly written as box of psi is equal to 0, where the operator box is given by d mu. So option B is the correct option.